Hello, everyone. This is the 16th IITT episode, another exciting episode, this time on offshore geotechnics with experts from around the world. I'm going to share my screen and introduce you. To Phil Watson, Shell Professor, Offshore Engineering, Director of Arctide, University of Western Australia. I was in Austria a few weeks ago. So, foundation design, site characterization, a real expert, and chair of this Offshore Geotechnics TC, which is TC209. Then Elizabeth Palix will take the floor, offshore technical lead for APAC at Électricité de France, another expert in offshore wind foundation and site characterization and foundation installation. Zack Westgate, again, Associate Professor of Civil and Environmental Engineering, University of Massachusetts in Amherst, offshore foundation expert and site investigation. And then we'll go back to France with Christelle Abadie, Research Fellow at Gustave Eiffel University in France, member of TC209, all of you are, I think, Offshore Wind Foundation. I'm so excited for this episode. Let's not waste time. I will give the floor now to our expert, Phil Watson. Phil, the floor is yours.
Thanks, Mark. Hopefully that is now
I'm going to mute myself, yeah, so that you don't have background.
No problem. That's showing that. Hopefully so. All right.
You're in presenter mode, Phil.
Okay. That's why it would change. Maybe that's working now or not.
Not yet.
It's loading.
Why would it change?
Don't worry, because the team can.
Yeah, that's okay.
Yes.
Yeah. Yes, that's now working.
It's working now.
Excellent. All right, we got there. Great. Thank you, Mark, for welcoming us tonight and for giving us the floor to talk about what we think is a pretty important topic, geotechnics for offshore wind. I guess I'm a little bit the appetizer tonight. Just going to introduce TC209 and set the scene a little bit. Our three speakers, Elizabeth, Zack, and Christelle, are really going to provide the best part of the show today in talking about their respective parts. So I won't waste any time. I'll jump straight in. So I'm really going to cover setting the scene. Before I do that, I'll just do a very brief introduction to TC209. So TC209 was once a significant committee and it fell away for a little while, but then was re-established in 2009 under the leadership of Philippe Jean-Jean. And under his leadership, it grew pretty rapidly, and we're now over 100 members. It's a very active committee with myself as chair and the executive, and we're pretty busy. And if you're interested in where our footprint is, then that's essentially it. So the red bits are kind of where we have active members. The orange is sort of where we have guest members in some of the countries. So it's a pretty active group. Some highlights of the group. So we do run an honor lecture, the McClellan lecture. The next of those lectures will be next year. Will be delivered by Philippe Jean-Jean himself in France. We run an international conferences every 2 to 3 years. They alternate between the International Symposium on Frontiers in Offshore Geotechnics, ISSFOG, and the Offshore Site Investigation in Geotechnics, OSCE conferences. OSCE was last year, ISSFOG is next year, and a little bit more on that in a second. In addition to the international conferences, we support a whole bunch of country-led conferences and symposia. Just this year, we anticipate sort of supporting the Vietnam Symposium on Advances in Offshore Engineering, which will be at the end of the year, the Indian Symposium on Offshore Geotechnics, also at the end of the year, and we are likely to run a second workshop on geotechnics for offshore wind in Japan. And just a few images, we ran a very successful workshop last year in October, the end of October, in Tokyo, with a couple of hundred members talking about geotechnics for offshore wind. We also support special issues, and we're just in the closing stages of a state of the practice journal series in ocean engineering. We're just finalising the last 2 papers, and then all the papers will be out, roughly 25 papers, again on offshore wind. So we're a very active committee. And while we think active, one thing just to promote is we are about to get really active promoting our next major event, which is the 5th in the ISSFOG series. Christelle and Elizabeth on the line are actively involved in this, along with other members of the committee. It'll be in June next year in Nantes, where Christelle is. It'll be a very well-attended event. The last one was in Austin. It'll be coming up. There's a call for sponsors.
Christelle, you didn't invite me.
You'll get an invite. You'll get an invite, Mark.
You're welcome to come and visit us for the ISSFOG conference. That'll be great.
That would be one.
I love this, TC. You're really very active, Phil. And I remember meeting you all in Austin here. I am in Austin, Texas, last year.
It's a very active group.
So I will try my best to join you in Nantes. Keep going, Phil. You know, this is interactive talk, so we can interrupt each other.
Absolutely.
A little bit.
Jump on in. As well as the call for sponsors, there is a call for abstracts. It's open until the end of May. So when you log on and you get this, there's a QR code, but certainly reach out if you have any trouble getting in touch. But we're looking forward to a really big conference, and we'll come back on this a little bit later on. So with that behind, I'm just going to spend a few minutes just giving a bit of a setting the scene in regards to tonight's talk on geotechnics for offshore wind. So very quick history. So about 1990, we had the first offshore wind turbine, which was in Sweden. 91 saw the first true offshore wind farm, which was in Denmark. And sort of since those humble beginnings, it was fairly slow initially to take off. But if you have a look at that graph on the screen there on the right, you can sort of see the exponential growth, both to sort of where we are now in 23, 24, and then we're forecast to be over the next couple of years. So thanks to Zack for providing the image, but that's kind of, you know, it's just growing. Short story is that it's here to stay. Like it or not, offshore wind is going to be a big part of our future. It's growing and it's here to stay. If you're interested in the history a little bit more, the last bit of promotion for TC209, I would say, is we did put a contribution into the time capsule project, which was presented a few years ago in Sydney. And that does provide a bit of a timeline on the renewables journey in Europe, Asia, and North America. We're still building that, but you can go to that to our website and you'll find more details. So a little on the history, a little about the future. So, I mean, the urgency to address climate change, it's clear, it's in front of all of us. If you're interested in a bit of a wrap-up, Dave White from Southampton gave an excellent rapporteur presentation after OSCE 2023, and really a call to arms for offshore geotechnics and the role we play in sort of the climate change effort. A lot of that through offshore wind. Using this particular graph comes from DNV. This now forecasts out to 2050, and it's essentially concluding or predicting that roughly 10% of total electricity generation is going to come from offshore wind by, I should say, 2050, not 2025. So that's kind of where we're heading. But I would point out that in this particular report as well, in this one, they were relatively pessimistic of what we can achieve as a society in regards to climate change. And actually, they were predicting we'd only get to about half of where we need to get to by 2050. So there's certainly room for improvement, room for more offshore wind in there. So it's here to stay and it's growing. Offshore geotechnics is pretty important in here. So if you read the press, you'll see that offshore wind is facing headwinds, so pun intended there. We see a lot of issues with inflation, supply chain reliability, and that has an impact on profit margins for major offshore wind projects. There's challenges around permitting, environmental regulations, etc., and that creates uncertainty. So you know, offshore wind does have some challenges as it moves into the next period of time. Geotechnics is a pretty major contributor to cost. through site characterization, offshore surveys, and all the associated works, foundation design, fabrication, installation, and then operations themselves. So if we want to help offshore wind be successful, we need to continually advance the technology to produce better outcomes. So it's a pretty exciting time as a geotechnical engineer and our support for offshore wind. And it's an urgent time, but there's a lot to do, but some big challenges as well. So a question you might ask is, well, we've been doing offshore stuff for a while, so what don't we know already? What's new? I mean, a couple of slides on this. So site characterization itself, well, it's well understood. We've been doing offshore site investigations for a long time. Wind is a bit different, but a couple of the key things is, well, you see developments cover very large spatial extents. So they're very wide, much bigger than a conventional oil and gas type development. Often these developments are in areas where you lack historical data, so you can't go to a shelf necessarily, find something that's been done before and use that. They're often in very challenging ground conditions. We've gone a little bit back to the future, where now we are looking at developments in shallow water, where the oil and gas industry sort of moved to deeper water some time ago. With shallow water comes more variable ground, and we also see new soils. I put brackets there because I'm not sure that they're actually new. We have seen a lot of this before, but the challenges they bring are certainly new. It's also said often that there's not enough boats. If you're going to have that many wind turbines and you're going to have a CPT per location, there's not enough boats in the world to do all the CPTs, and there's not enough labs in the world to do all the tests that they're doing. So how do we solve this? And I guess the future, maybe it's going to be through quantitative geophysics is going to play a bigger role. We might see data science step in more and more. More groups are working on data science-driven solutions. We might see more leveraging of large databases. So there is a lot of historical data. Can we bring it together, perhaps to reduce the call and demand on our labs, so projects can do fewer lab tests and do there? And in reality, we need it all. We need it all and we need more. So there's heaps to do in this space. If we look at fixed wind, so fixed wind today is dominated by monopiles. Probably 80% of offshore wind turbines are sitting on monopiles. But you do have significant numbers on pile and suction bucket jackets and gravity structures, certainly in the early days. There's a long history of offshore foundation design, so we've been doing this sort of work for a long time. But in regards to offshore wind, it's really complemented by new challenges and new research. So you see programs like the PISA JRP, and there are others where sort of it's new research targeted at offshore wind, and you see local practice stepping in. And an example of that is the recommendations that have been developed and put out in France for fixed offshore wind.
Phil.
Yes,
Phil.
Mark.
Sorry to interrupt. Can you zoom in on that photo? I just discovered that these were not ants.
No, they're not ants, and if I zoom in, I'm going to muck up the screen, so I'm not going to do that. But they are not ants. That's the size of a turbine. I grabbed this off offshorewind.biz. It's a pretty new photo. This is for ocean wind up off the US. So
this is amazing. Yeah,
this is pretty new. So these are big.
You cannot enlarge the photo for the recording.
Not without risk of mucking it all up, Mark. I don't trust my IT skills.
Okay.
But it'll be online there.
I did on my screen. I did it on my screen. So
maybe it'll show you. Okay.
I wonder if the recording will pick on that.
No worries. So even while we've done a lot of work and we've got our recommendations, there's a lot more work to do. We are seeing a real push towards shorter monopiles, so reducing the LND, pushing into territory we haven't seen yet. We see more questions around rate effects and partial drainage and cyclic loading and fatigue. These aren't solved for offshore wind. And we have issues about installation reliability and noise. Lots of concerns out there about the noise associated with the installation of the monopile. So a lot of work goes into how do we reduce that noise. So fixed wind has been around for a while, but there's still lots and lots of work to do to help us get there. And lastly, floating wind is coming. So we see lots of demonstrators at the moment. So here's an image from one that we have a little bit of involvement with through my group here at UWA. This is the Tetris bar development. There's a little image of it, but that's what it looks like in the field at the moment. So this is out there at the moment. There's a number of them as demonstrator options. What I would say is sort of anchoring options for these are pretty well studied. We've been doing this stuff as well in oil and gas for a long time. Plate anchors, drag anchors, fairly conventional solutions, although need to be proven in new soils and in new areas. We do see new challenges, but we see new options. And again, commas for new, because I think a lot of these things are not new. But here's an example: helical anchors for offshore floating wind. That's being looked at by numerous groups around the world. We also see reliance or people looking at shared moorings. So in past, where we looked at individual moorings for individual floating facilities, maybe we can't afford that in future. Maybe we need multiple moorings. So one mooring will hold 3 or more turbines and support them down. So that raises new questions around loading from different directions and how those co-supported moorings will behave. And then you also have issues or questions about reliability. If you have an arrangement like the one here on the right, where you have maybe multiple moorings, what happens when mooring lines break? They do occasionally break in practice. For an oil and gas facility, maybe you would have multiple mooring lines from each direction and you can cover redundancies. You don't have that same redundancy in these kind of arrangements. So if that line breaks through fatigue or some other issue and that turbine moves, how does it behave? So we start to see more challenges in this space. So hopefully
shark attack.
Shark attack, poke out the line. So hopefully that's whet the appetite. I'm going to hand over now to Elizabeth, who will give a perspective from being a wind farm developer. Zack will talk about some new challenges facing offshore wind, and then Christelle will bring it home and talk about research to support offshore wind. So I'll hand back to you, Marc, to hand on to Elizabeth as our next speaker.
This is great introduction. I have to say one thing that caught my attention when you were talking about the history. There's no history. And when I give a lecture, I always say never, ever start solving a problem before SOLGE. The SOLGE is the principle I keep preaching about. So you collect soil, loads, geometry, and history. And here you don't have history in the middle of the ocean. So it's a big challenge. Elizabeth, the floor is yours.
Yeah, thanks, Marc. So thanks, Phil, for the introduction on the offshore wind. And one point I wanted to emphasize is also the increase of the size of the wind turbine. So it's increasing very, very quickly. So as of to date, we have turbine installed up to 14 megawatts. And in the 30s, maybe it would be over 20 megawatts. But we started like at 2 megawatts and it was not so far away. And just for another idea, what does it represent in terms of foundation? For 9.5 megawatt, the foundation was a monopile on the Arcadis, and it was already a 9.5 meter diameter monopile and 2,000 tons. So we can imagine what it would be if we are going to tackle the 20 plus megawatt wind turbine. One thing also that will increase with time is the installation vessels that will be needed to install those mega turbines. So you can see there the difference in size of the jackup. So it's a vessel with legs that is needed to install those turbines. And another aspect also that Phil mentioned is that the water depth we are looking at is also increasing. At the start, we say every countries were looking after the easy area, I would say close to the shore, in something like 20 to 30 meter water depth, where monopile was the preferred, I would say, foundation. But more and more we are facing some new ground condition, more challenging, but also higher water depths. And at some stage, as you said, Phil, we will need to go for floating. It's not quite clear what is the water depth range that will be needed to go for floating, but we are getting ready to go to this stage. So floating is and big water depths is, as you mentioned, Phil, it's not uncommon in offshore geotechnique because the oil and gas drive us to even much bigger water depths. But what is new for the offshore wind is the number of assets you have offshore. So in the present case, it's a layout of a project in the coast of France where you have 80 foundations. So it's not only a foundation for one asset, for one platform, but for 80 turbines plus offshore substation. So we have the foundation for the turbine, as I mentioned, for the offshore substation. We have the anti-array cables between turbines and the offshore substation, then the export cable. And to go to the shore, we either get excavation or horizontal drilling technology. We also have some jackups legs that will touch the ground. So that drives to challenges that are particular to offshore wind, like the high number of cycles that will be applied on the top of the foundation. So in the order of magnitude, we are speaking about 10 exponent 7 number of cycles. So what is the effect on the foundation and the soil structure interaction? At the bottom of the foundation, there will be also some scour, global scour, but also local scours that will develop. So we need to see whether we accommodate in the design for the development of the scour, or if we need to prevent the scour to develop. For the installation of the cable, we need special tools like a plow or a jetting system or rock wheels to do the installation of the cables to a depth where it will be protected from threat like anchors. And for the installation with jackup vessels, we need also to assess what will be the penetration of the legs. And we're speaking about several meters in some cases. So it will have some impact on the nearby structures, but also on the strength of the ground. So the duty of an offshore technical engineer, it's all over the length of the project. So from the early start, where you decide whether you want to do the project or not. So you're looking after the main geohazards and what are the difficulties of the site, but also, of course, during the development, where you will need to assess all your ground condition, but also all the risk, and try to develop an optimized solution. And up to the operational phase and even the commissioning. So you will really want to try to find out what will be the optimum between having a foundation that is as optimized as possible and to lower the risk. And what you want, particularly for an offshore wind project, is to minimize the time you will spend offshore. The jackup that I showed previously, for example, we're speaking about a price of 300 kilo euros per day. So you really want to minimize the time you will spend offshore. And it's the same thing for the site investigation. You want to find out the optimum. So to get a good ideas of the ground condition, ideally you want to get a geotechnical 3D model. So for that, you will get your site investigation with the geophysical surveys plus the drilling surveys. So we're speaking about a geophys survey, it's about 30-40 kilo euros per day. And for drilling vessels, it's about 40 kilo euros per day. So you want to find what will be the optimum site investigation that will gather all the information you need to mitigate your risk and to do your optimization of your foundation. So you need to leverage the ground complexity, the optimization, the risk mitigation with the cost, and also the planning. Also for some areas, you're not able to work during the full year. So you have a limited window, I would say, to run your site investigation. So I'm going to present a particular project. So it's the first offshore wind project that have been developed on the French coast, the Saint-Nazaire project. So you already saw the layout with the 80 location. So it's situated on the Glauconite bank, and at the north you have a paleo channel passing through. Initially, we thought that we could do the investigation at only 50% of those locations in order to, again, optimize the time spent for the surveys. But considering the difficulty of the ground condition, the difficulty to interpret the geography results, we at the end of the day, we did one bore per location. But there are some cases where you can do 50% or even less, preventing that you have a very good geophysical interpretation. Yes.
So
Yes,
the
Marc.
Calcarenite is a rock? Is it considered a rock formation? I see dolomitic below it.
Yes, it's rocky bed. Yeah, we have some confining compressive strength of about 10 to 100 MPa on this site.
Okay, so you're talking
But
80,
of course,
80 turbines, 80 turbines.
Yes.
Floating, right? So you're anchoring in the rock.
No, it's fixed bottom. It's fixed bottom. As you will see, we installed some monopile. Mm-hmm.
So they're all monopiles.
Depth, and the water depth is between, let's say, 12 to.
Yeah, I couldn't see that.
meters.
I zoomed on it, and yeah. So you're talking in orange about 10 meters all the way to 50-meter deep.
Yeah, correct.
I'm just trying to clarify the geometry. Okay, good. 50 meters. Wow. Keep going. Sorry to interrupt, but I'm trying to be the viewer inquirer. Keep going.
No, but things that
I like it. I like it.
Yeah. So one of the challenge on this site is also that well, previously many monopiles have been installed, but mainly in sand and clay, but no one were installed in this kind of rock condition, calcareous condition. So we didn't get any standard providing some recommendation toward the design of a monopile in this kind of rocky condition. So we didn't know how to get a simplified model to do the design of the monopile. In the literature, for more slender piles, you have several kind of springs, I would say, that could be used for the lateral resistance, but we didn't know which one would apply to a project. So, and by using the left one or the middle one, we would have come up to a very different size of the monopile. So considering the need to do the optimization of the pile for 80 foundation, it's not only one. It's not like if you could say I can add a few meters of pile. I mean, it's always multiplied by 80. Then we decided to go for onshore pile test. So you can see there are pictures at the top of the installation phase. So we also wanted to try the installation, the driving in similar rocky condition, and also the drilling. So you can see there it's an offshore drilling tool that were used onshore. Quite a challenge with all the equipment to bring enough water to make it work. And at the bottom you can see the loading phase. So we applied a load up to 2.5 kilonewton at 5 meter height to reproduce the moment that the turbine would apply on the monopile. So we made a lot of
static,
observation.
Right?
Both static and cyclic.
Static or cyclic?
Both.
Oh, cyclic. I see
it now.
We need
both. As I said, the effect of cyclic loading is very important for the wind farm. So what we found out is that, of course, the rock is not behaving like soil or clay that will get back at the back of the pile, but we have a gap when we apply significant loads. We are crushing a part of the rock close to the pile, a bit like in chalk. So you have a completely crushed material. And we are also developing cracks in the rock. But what was interesting, in blue, you have the cracks developed during the driving, and in red, what was left after the loading. So was interesting to see how the cracks could develop during the loading. And we acquired a lot of information through the cyclic test. So we then implemented all the observation in numerical model to be able then to do the extrapolation to the real size of the monopile. So all this information have been directly used in the design of the wind farm. But of course, there is a timeline of R&D and there is a timeline of a project. So we've not been able to implement all the findings that we then acquired through a PhD. But it's good also that we are able to dig a bit more, I would say. And we developed with Anaïs Lovera, who did a PhD on this subject, geological model that we're going to use in the next project of the same kind. So Phil asked me asked me the question, what was the point of view of a developer towards R&D, and Zack and Christelle will talk about particularly Christelle about R&D later on, but it's very important for us. As you can see, the Saint-Nazaire project was very first of a kind, so we had to do something. We had to do our R&D, but it's not always possible through a project to do this kind of things because of the planning. So we also believe that it's important that all the developers work together with through joint industry project, and Christelle will present a few of the GIPs that exist in the offshore wind community.
Elizabeth.
So at the end of the day, with this, yes, Marc.
This is so exciting to me. You don't know how much. If you know, maybe I'll share a couple of slides later, but you know, the behavior laterally loaded piles. I gave a lecture at Urbana-Champaign, and I developed when I was a PhD, because I saw PhD thesis. This is exactly what my PhD was for: cyclic loading and lateral behavior. Let me do it now. I will share my screen. But later, when you're done. Keep going.
No
I love
problem,
it.
Marc.
Keep going.
Good to hear. So to go back to the Saint-Nazaire project, at the end of the day, we decided not to drive the monopile due to the risk of lateral pile buckling. So we had three types of installation for our monopile. Either there was no rock, so it was a kind of a classical fully driven pile. Either we had enough rock thickness, so we did some drill and coated pile, so with the coating only on the external annulus, or the thickness of the rock was not sufficient to get the pile completely embedded in it. So we did some drilling through the rock, then driving of the monopile and coating on the annulus. And the decision of doing one of those were really different depending on where you were on the wind farm. That's why also we had to do one borehole per location to really assess which type was the best suited. And there's last slide just to show you the installation, some tools. So the hammer that were used was a 4,000 kilojoule hammer. The drilling machine, it was first of a kind or so, because it was a vertical boring machine that were used for the first time offshore at sea. So the salt was one of the challenge, I would say, for the design of this tool. And on the right, you can see the jackup with all the tool, all the equipment, like the monopile, the transition piece also at the back in yellow. So it was a very successful installation sequence. So very happy that was the first French project in very challenging condition. It went well.
Elizabeth?
So, yes.
Couple of questions. So how deep was the monopile? It doesn't show here. And how much time it took to drill 7.7 meter diameter pile.
So the length was really depending on the type of condition. The longest one was the driven one, something like 30 meters depth. And the smaller one were the one embedded in the rock, so something like 20 meters, I think. And regarding the time,
so you drilled under rock
again.
Yeah, you drilled under rock 20 meters with a diameter 7.7 meter. So how much did it take for each monopile? 3 days?
Yeah, well, about 2 to 3 days, yes. Of course, the easiest one is fully driven. So in 24 hours, you can sell a monopile. After you have the time to go from one location to another, and the weather condition is really important for that, because you cannot do this operation in any weather condition.
And were the work done in November, or which time of the year?
Well, it was through two seasons. I mean, I think that we started something like in May, and we finished the May after the year after. So 1 year in total, and we worked. We've been able to work over the winter.
Yeah, I'm used to the Mediterranean. The calmest time is November. But this took 2 years. Keep going. Sorry to interrupt. So exciting.
No, it's done for my presentation. So I will let the floor to Zack.
All right, let me take over here.
The floor is yours, Zack.
All right, you should be able to see the presentation. Let me just put it in presenter mode. All good? All right. Let me just get my pointer in case I need it here. So laser. Okay, so as Phil mentioned at the beginning, I'm going to be talking about new challenges with offshore wind. This is mainly around the area of challenges related to the seabed, and others covering more of the foundation side of things. So we'll start off talking a bit about the East Coast in the U.S., where due to glacial geology and just variable conditions, we've got all kinds of exciting, I guess, soil types that we can talk about here. I'll move down to Australia, where we have some experience in carbonate soils that will certainly have an impact on how we go forward in the southern U.S. I'll then move up towards Northwest Europe and follow on from Elizabeth's talk, focusing more on the low to medium density chalks rather than the calcarenite that she was just speaking about. Then we'll head east over towards Taiwan, where we're seeing issues with piles disappearing below the seafloor. And then just finish up on the U.S. West Coast, talking about some of the geohazards related to floating wind and anchoring. So site characterization, as Phil alluded to, it's certainly a global challenge. We see this pretty much everywhere. Part of it is simply because we're characterizing massive sites. It's a little bit misleading sometimes to be looking at a map and drawing boreholes and CPT locations without really getting a good perspective on the size of the areas that we're characterizing. So I put site in quotations because it's more of characterizing just massive tracts of lands. And just to give a bit of context, here's a few example island areas. We're literally characterizing islands. Multiple towns, multiple counties, several hundred square kilometers each. So it's going against the conventional wisdom of how we approach site investigations. And a lot of these sites have a lot of site variability, both in the vertical and lateral direction. And one of the challenges, of course, is trying to characterize sites to the degree that we used to for oil and gas. And we just can't approach it that way anymore. So there needs to be a bit of a transformation in how we approach site characterization in order to meet development timelines and ideally expedite those timelines so that we can move towards a cleaner energy future. So this site here is about 20 kilometers. Yeah, Mark, go ahead.
could you explain to the viewers how was this graph obtained, just quickly? Because
I
to me
stole it from a
too.
project report. No, I pulled it out of, it was published in the De Groot keynote from OSIG, but this is a seismic cross-section. It's been interpreted to identify geological reflectors and start putting some, basically some stratigraphy interpretation to what is essentially a very large and complicated site. As you can see, you know, we've got—
So it's a combination of CPT, geophysics.
It is, yeah. So this is
very
sub-bottom
nice.
profiler data. Yeah, and you can see a little bit of cone penetration data where we have it that really, you know, ties in reasonably well with the seismics. But when you think about, you know, putting foundations every couple of kilometers spaced, you know, across this site, you can see there's obvious challenges with selecting one foundation
It's a
type
great
and then
method.
obviously
Yeah.
designing something to meet that. This
So
particular site—
the bold line at the top is the bottom of the sea.
bold line at the top is the seafloor. Yes. Yep. Yep. Yeah. So there's some superficial sands at the site, Holocene sands, and then we get into quaternary deposits, and then below the blue reflector here, we're sort of into older Cretaceous deposits here. So.
And what are the numbers on the left? 0.05, 0.1, 0.15.
This is in two-way travel time. So this is the time it takes for the seismic waves to come down to the reflectors and back up. And you can see sort of a depth scale on the right where we've done a conversion. Each black bar here is about 20 meters. So we're looking at about 100 meters total depth from top to bottom of the image.
Now it's clearer. Thank you.
Sure. So yeah, I mean, general sense of urgency, you know, how do we characterize these sites? How do we expedite the timeframes? You know, part of the site variation is due, at least on the east coast of the US, to a combination of changing sea levels. So millions of years ago, the sea was much lower. And the areas where we're putting turbines right now was basically on land. So we have all the, you know, land-associated seasonal cycles, freeze-thaw cycles, desiccation, et cetera, Hudson Valley River runoff that create sort of these paleo channels and gullies that create the site complexity. And we also have glacial retreat. So we've got the Laurentide ice sheet delineated here. We've got the Ionian and the Wisconsinian. And so these leave terminal moraines and recession moraines, which basically leave us with a whole pile of stuff. Cobbles, boulders, which can lead to challenges with site characterization and also foundation installation. So the boulders, you know, we've gotten pretty good at finding them. We can determine where they are, how deep they are, how big they are. But you know, when you're finding boulders 6 to 15 meters in diameter, you know, it poses obvious challenges for pile installation, but also for cable routes where you can't necessarily drag a plow through an area with, you know, 0.5 meter to 1 meter sized boulders. So there's mitigations that we can pursue. None of these are cheap. We can either pick boulders off the seafloor one by one, or we can, you know, basically drag plows across the seabed and clear a path for an export pipeline or an export cable installation. Again, not cheap and certainly not necessarily environmentally friendly. So I want to spend a few slides on glauconite sand. This is sort of one of the newer soil challenges that we're dealing with. It's a bit of a misnomer. It's actually not sand. It's not really soil at all. It presents as a sand-like material, but it's essentially a biogenic substrate that forms around some kind of, you know, biological element, whether it's a fecal pellet or a foraminifera. It's iron rich, so eventually through the maturation process, it can become magnetic, which that means it's relatively high in terms of specific gravity, up to values of 3 or so. There's a few terms up here: glauconite, glauconite, glauconitic, you know, morphological, mineralogical terms that partly depend on how much glauconite's actually in the deposit. Orthogenic glauconite is essentially still in situ, so it's sitting where it has formed over the years, versus allogenic, which is reworked and has been transported across, say, the continental shelf. It forms over the course of about 1 million years. So you got to have sort of the perfect recipe for formation, and it's got to be just sort of right at the sea floor surface to happen. It eats up aluminum over time. It produces potassium, produces iron, again, becomes a bit magnetic, but you can see a transformation in the particle morphology here. And eventually we end up with essentially these shiny, low bait pellets that look like, sort of popcorn kernels that are still ready to pop. And that's essentially what happens when you start driving piles to them. They crush and turn into a bit of a geotechnical nightmare. So how do we identify glauconite is sort of the first challenge. So far, it can't be done.
You gave me an idea.
Yes. You're going to share.
So we start with consolidation using cementation, then consolidation using freezing. Now you can do here consolidation with a magnetism.
It's possible. It is possible. Yeah. So identification.
I wonder how magnetic it is, but they look pretty magnetic with the form, the shape, the color.
They are. You can use a magnet and separate it from other minerals, quartz, sand, if you're in the lab trying to create samples of this to test in its more pure form.
Keep going.
But yeah, so CPT identification is sort of the first tool that we might use to see what we're pushing cones through. Generally, we see high cone tip resistances, 10, 20, 30 MPa. Also high sleeve friction, but characteristically high friction ratios, so values of 3, 4, 5, and even up to 10 or so. U2 values, it could be extremely high positive pressures, but also they could be high negative. So you can find dilatant deposits, which, combined with high tip resistance, high sleeve friction, and dilatancy leads to pile driving challenges. We also see evidence of glauconite just from the pile rod or cone rod itself. So just above the friction reducer, you can often see a bit of a smear of crushed glauconite. You can see the green sort of ribbon of soil here. The green is just due to the oxidation of the iron. But once you get it back into lab, of course, you can then characterize it with more traditional tools like XRD and XRF and get a handle on what the mineralogy is. And then you can sort of classify where it is on the maturity scale and how much of a problem it's going to be to your project. So still on the subject of CPTs, we can attempt to use soil behavior type tools, the Robinson chart on the left, the Schneider chart on the right, to try and classify the glauconite sands from the get-go. However, if you look at particular units, sometimes they might present as a sand on the Robertson chart. If you're using cone tip resistance and friction ratio, but then when you start considering the pore pressure measurements, you might interpret that as a clay with the Schneider chart. So potentially misleading. We don't necessarily, it's not necessarily reliable to use established soil behavior type boundaries for these new soil conditions. So a few of us have established a JIP called Piling in Glauconite Sand. It's led by NGI. It involves a few academics listed there. But the idea was to try and drive some piles into glauconite deposits onshore and get an understanding of what the risk is for pile driving. And as part of this, we managed to pull a pile or two out of the ground. You can see some example photos here of the crushed glauconite adjacent to the pile after it was extracted. And then, of course, scraped from the side of the pile. We did something similar with Shelby tubes pushed down along the inside of one of the larger piles that we couldn't extract. And you can see, of course, sort of the night and day between the crushed glauconite zone and then the less disturbed surrounding glauconite. And we're trying to replicate that crushing process in the lab. This is just a PSD plot here showing some natural glauconite sands down here, which have a little bit of fines. But then if we put them in a ASTM dispersion cup and mix them for, several hours, we can get significant increases in fines and then clay content, which has obvious implications on changes in behavior, including plasticity and strength and drainage. So the JIP is still going on and is trying to answer some of these questions related to pile driving. So just moving a little bit south along the U.S. East Coast, we are getting into carbonate soils, so calcareous carbonates. There's even some limestone reef the further you go offshore Florida. And of course, we know from decades of experience in Australia, carbonates are subject to high degrees of cyclic degradation, both at shallow depths. So this is some T-bar penetration tests, cyclic T-bars, which show very high sensitivities. but also through DSS tests on deeper samples, which show, the higher susceptibility of glauconite sands relative to, carbonate sands relative to non-carbonates. And of course, we know why this occurs, right? We have very high internal void ratios for carbonate soils, high void ratios of the soil composition itself. So under cyclic loading, they crush, they compress significantly. And we need to certainly think about that as it relates to, the different types of cyclic stress ratios that we'll be having to design offshore wind turbines in Australian and US waters relative to historical experience with heavier oil and gas structures. So just touching briefly on chalk, I'm certainly no expert in this, but building off of Elizabeth's discussion on some of the fractures and issues related to pile driving. When you're driving piles into chalk, similar to glauconite, you form sort of a thin crush zone around the pile itself. In the cases of chalk, it's essentially a paste or putty-like material, very low shaft friction, 10, 20 kPa, say. So you can get into issues with pile runs, obviously, long-term axial capacity. But because of the fractures essentially extend, multiple diameters away from the pile, you also have a significant issue with reductions in lateral stiffness. Intact chalk itself behaves, relatively brittle at fairly low strains, but then it significantly strain hardens. And we've seen quite a bit of activity associated with JIPs, which have tried to, further understand chalk behavior and create new models to basically represent things like shaft friction along the pile wall, and also things like static and cyclic lateral models there. So we've come a long way in terms of understanding chalk, but as Elizabeth has pointed out in her presentation, there's still a few challenging soil conditions up in northwestern Europe. And now moving east out towards South China and Taiwan. So we've seen in the news, several of these issues with piles running, and in some cases completely disappearing. In one case, 3 times on one project. The main reason for this happening is that you've got a lot of sediment load coming off of the major river systems in China. In the case of billions of tons of sediment per year. And that combined with the strong currents from the Strait of Taiwan between China and Taiwan itself, we see these sort of seasonal depositions of essentially layers of clay, silt, and silty clay. In some cases, we have quite strong layers over relatively weak layers. So not only does it pose an issue for pile runs and axial capacity, but also for jack-up stability in these areas. And so we've got sort of the perfect recipe for low axial capacity pile runs due to easily triggered liquefaction, and of course the very heavy monopiles that are needed to get down to the depths to generate the axial capacity. And some may be blaming port site characterization, but obviously it always depends on who you ask there. So moving back to the US, now moving over to the West Coast, where we'll be shortly dealing with challenges with floating wind and designing acres. There's a couple of call areas right now offshore California. One is offshore Southern California, where we have the Morro Bay and Diablo Canyon call areas. And then further up the coast, we've got the Humboldt call area off of Eureka, California. So these 2 images, which are taken from a desktop study by RPS, show the level of seismicity in the area. All these dots represents a seismic event from the past. And you can see, it's primarily due to the level of faulting and the major fault systems that run through this area. So we certainly have the triggers for landslides, and we also have sediments which are ripe for moving down the seabed slopes here. So we've got a lot of unconsolidated quaternary sediments and sort of pink here in the Morro Bay and Diablo Canyon area. We've got significant river deposits from the Eel River accumulating relatively quickly. So lots of underconsolidated sediments, again, sort of ripe for subsea landslides. And we can look to the evidence of the past here. This is just some bathymetry of the Morro Bay and Diablo Canyon area. And you can see, obviously, there's a lot of canyons here. You can see some evidence of past runout. And you can go back to the geological literature and start putting some names to some of those. And this is very similar to what we see further up the coast offshore Eureka at the Humboldt call areas. So lots of challenges related to design and selection of anchors in these areas, not only in terms of, what kind of anchors are we going to use to withstand landslides, submarine landslides, but also areas where you have bedrock outcropping at the seabed. So I guess I'll leave it at that. I know Christelle has a bit more to talk about in terms of anchor selection design, but that's a bit of an overview of some of the newer challenges that we're facing with offshore wind.
A true international presentation, Zach. You've been all over the world.
Thank you.
Christelle, the floor is yours. Such an exciting episode.
All right, thank you. I'll wait for my screen to start sharing.
Yep, you should be able to now. Okay.
All right, super. All right, thank you very much. First of all, thank you, Phil, and the TC209 for inviting me today. And I hope that during this presentation, I will echo some of what Phil, Elizabeth, and Zack have been presenting, but showing the perspective of the researchers and how we come to support the development of offshore wind throughout the years and the different challenges that we've been facing. So starting off, what I would want you to take out of this presentation is how much we've achieved so far, but also how much we remain to how much we have to achieve in the future years, and how exciting the field of geotechnical engineering is, and offshore wind is. I'm certainly very excited about everything that we're doing at the moment. So I chose this slide to kind of illustrate everything that I'm going to be talking about, with bar charts that shows you how wind has evolved from 2011 to 2021 and how much remains to come. Now, I choose 2011 because this is when I started my PhD. And at the time, offshore wind was not a viable energy solution, and it was not financially viable. And 2021, which is just around the corner, saw massive developments throughout Europe. 2026 is going to see a big evolution throughout the world, and we're really expanding in new site locations with new. And 2031 will be what I hope to be the start of a very big adventure for floating wind. So all throughout that, the objectives have remained the same. It's been to reduce cost and extend service life of offshore wind in order to reduce the financial and environmental impact of offshore wind and make it possible compared to other energy sources. Bring it further offshore where the winds are steadier and stronger, and where we can design for largest turbines. Obviously, we've got to support them. That's a challenge. And produce more energy. And nowadays to adapt for new world locations, which Zack covered pretty well. So the role of R&D in all this
Christelle?
Yeah.
Could you go back one slide? Just to clarify, the yellow is, what are the numbers on top of the pie charts?
Gigawatts.
4.35.
Gigawatts.
So,
it's written in the little
gigawatts? Corner. Okay.
Yeah. It's written in the top left.
Is it mentioned? Oh, down there. Okay.
Yeah.
So the yellow is planned?
Yeah, the yellow
and the
is...
blue is achieved?
The blue is what's achieved.
Okay. Thank you. Keep going. Sorry to interrupt.
No problem. So the role of research and development in all this is to permit those developments by, in the background, developing the new and improved design methods that enable to further optimize the geometry of the foundation and therefore save costs and extend the service life. And also to enable the development of new foundation systems. And that is important because if we have a mix of foundation, we can adapt to more word location and different soil conditions and offshore environment. And to do all this, we need to verify the foundation design through testing and numerical modeling. And this is where the challenge comes, because testing real piles, large scale offshore is nearly impossible because of cost and risks. So we've got to find other ways to generate data, and that is through a combination of physical modeling, mostly centrifuge testing, but also 1G small-scale tests, element testing, and field testing onshore, as Elizabeth showed earlier. And all this is used to fuel into numerical models that are validated through those data and are then used to provide the knowledge and the new design guidelines and new design methods through validation and also understanding the behavior of the foundations. So in this talk, what I'm going to try to do is to go down memory lane, really, and show how research has been supporting the development of offshore wind, what we are currently doing at the moment, and how much remains to be done in the near future. I'm sure if you ask me again in a couple of years, I'll have more things to say, because we are constantly increasing the size, as Elizabeth was showing, and that comes with new challenges every single time. And in this talk, I'm exclusively going to be talking about foundations, but a note there that our colleagues working on cables and site investigations, and also installation vessels, in particular the SPATCAN foundations, is also important, but I'll focus on foundations. So research in offshore wind started in the early 2000s with the very first developments of offshore wind farms. And the main focus was really to enable this technology to become commercially viable. And therefore, the main focus was to reduce the costs and enable to design for larger turbines. And at the time, what was commonly agreed on is that our knowledge and skills derived from oil and gas was not sufficient for wind turbine, and the big urgency was to develop new design guidelines and design method to be able to develop robust design for monopiles mainly. And there was a little bit of work going on in the background on cyclic loading, coming up with a very fast empirical model for cyclic loading. And that was a fairly successful story, because in 2017, the first a non-subsidized wind farm started to arrive. And even in the eye of the BBC, the geotechnical engineers played a fairly big part in this. And that was basically achieved through joint industry project that basically linked academia to industry with some very successful projects such as PISA and SOLSIP that enabled that big push towards this 2017 years. Right, so what comes next? After that, the focus, if I may characterize, like simplify it, comes into first continuing to further optimize the design of monopile, but second to diversify the mix of foundation that's available to us today. And that's mostly focused on developing offshore wind in the North Sea at the time in the mid-2010. So let's look at the first one. The primary challenge once the design to ultimate capacity and small strain stiffness was achieved was to tackle cyclic loading. As you refine and optimize the geometry of the foundation, cyclic loading may become a problem. And in particular, you may see accumulation of deformation that may push the turbine, the foundation to tilt And if your foundation tilts by even just a slightly bit at the bottom, this very long mast is going to tilt by a lot more, and you risk that the blade catches the mast and then the whole turbine catches fire. So we're playing here with very tight thresholds of rotation for the monopile, between 0.25 degrees and 0.5 degrees, whether you're looking at the whole life cycle of the foundation or just the service life of the foundation. And the aim goal for all the researchers and developers around the world is to be able to predict this very long cyclic signal that you have that can reach up to 10 to the power 8 cycles of cyclic load history. And there are a lot of endeavors throughout the world that took place in the spectrum. I think we're starting to see some really, really interesting ways to model cyclic loading. We're at the stage where I think we need to bring it home and agree on one technique that's good, with the caveat that I think we're still a little bit struggling with how we can calibrate those models with parameters that are relevant to the offshore wind industry and the tests that are available from site investigation. But I personally worked on the harm model, and the main objective in all this was to translate that moment load history into the displacement of the pile throughout its lifetime, to be able to predict the residual rotation of the mast at the end. And that's challenging because you have to model 10 to the power 8 cycles, and you would prefer not doing that empirically. So 3D FE models, forget about it. I'm not going to be able to do this with a cycle by cycle model. We need fast routes. So some people investigate how to boost up constitutive models for 3D FE. Some of us, and that's the case of harm, work on 0D and 1D model. I think we need all of that. And that's an exemplar of one model that can achieve that. All right. The second.
Christelle,
Yes.
sorry
Yes.
to interrupt. So important. Can you go back 2 slides?
2 slides. This.
Yeah, maybe one more.
Here.
One more.
This one.
Go back.
Back. Here.
One more. Yes. If you look at this picture, oh, go further one. Yes, this one. So I'm thinking this is not to scale, right? The monopile with the loading.
No.
That it's as a recommendation, it's very important to have it to scale, whether it's the geometry, because the monopile is so tiny.
The geometry is to scale. The loading,
Wow.
I wouldn't even know
loading
how
is
to put
not.
the loading. Huh?
So the wave action, and this question is not for you, but to all our guest speakers. Which load is governing in general? Is it wave load, wind load, emergency braking load? Because I've done wind turbine design onshore.
I think I'll let
I want
Elizabeth
to
answer that. What I've seen is that it changes depending on the site. But Elizabeth, I'll leave that to you.
Elizabeth, if you could, because we didn't touch this subject yet, but it's important to explain to the viewer. Go ahead, Elizabeth.
Yeah, it can depend from one side to another, as said Christelle. But as you said, Marc, the emergency stop is one of the most severe case.
You're muted.
Yeah, so when you have the emergency brake, that's the highest peak of load on the
Yeah, but
moment
that-
on the
That would be
monopile.
your ALS design, which you get from your monotonic response.
Yes.
But once you've optimized for that, you may find that you get changes in stiffness and accumulation of rotation due to
Cyclic.
So you need
Yes.
to account for all those conditions.
The idea is to explain that it's so, well, not so complicated, but it's pretty complex to solve the loading issue for the design. Yes,
Yeah,
keep
for
going.
the integrity of the turbine, you need to ensure that the rotation is less than 0.5 degree. That is not so much, and already you have some inclination due to the installation. So between the moment where you have the wind turbine that is installed to the end of the lifetime of the wind turbine, you maybe have only 0.25 degrees of accumulation of rotation left. So it's not so much.
Yeah. All right. So the second challenge that I see we are currently working on is installation. So both Zack and Elizabeth touched a bit on installation challenges and challenging soil conditions. But even before we go to challenging soil conditions, pile driving, as we currently do it, is very noisy, with some environmental damage for marine life. So reducing the noise level was a big priority. But also understanding how the installation process can impact the lateral design of the pile, and being able to predict installation fairly accurately is important. And this has triggered a number of projects through across the world. And one thing that I'm particularly close to is the development of equipments which are specialized equipments for centrifuge modeling. These projects take a few years to put together and enable to develop a pile hammer that can work in flight on the centrifuge. If you're interested in knowing more, I recommend that you watch one of the episodes, one of the earlier episodes from TC104 on physical modeling, but that's challenging. And that's an exemplar of the one that's been developed here at University Gustave Eiffel to enable installation of pile in flight. As I'm aware of, I think there are only 2 in the works that are currently in use. One here, the other one in UWA. And that enables to really study the impact of installation on the response of the pile after installation, but also to refine the installation prediction. And then finally, for design in Northern Europe, installation in weak rocks and chalk is essential, and Elizabeth covered that, so I'll move on. And from then on, we're pretty much set into improving design guidelines for monopiles. What we now need is to increase the mix of foundation available to us to adapt to different soil conditions, whether there are boulders or whether we can use a more silent installations through suction caisson if the soil permits, this sort of thing. So the first type of foundation that's available to us is a gravity base. There hasn't been much research, or certainly not as much research done on gravity-based foundation for offshore wind than for monopile or jacket piles or suction buckets. But there is a little bit done on this, especially because it's relevant to both offshore and onshore. Onshore gravity-based are the preferred type of foundation. So it's interesting to study it. And most importantly, it's important because, as you can see on this figure that was given to me by Elizabeth, actually, those foundations are massive. It's reinforced concrete, so it's not particularly good for the environment. And any optimization of the geometry is welcome. And in this project, what we're trying to do, so that's work that my PhD student is doing at Cambridge University. And what we're trying to do here is to really elucidate the behavior of the foundation under controlled cyclic lateral loading in order to understand which part of the soil are the most mobilized and optimize the foundation based on that. And that's the results of one of the very first tests we did on a traditional shallow foundation, showing that rotation can become an issue after a few cycles. So that needs to be looked at properly. So that's an exemplar on gravity-based. The following big push that we've seen over the last decade is on suction caisson, with massive achievement in that field. Unfortunately, I've not participated to a project on suction caisson, but I'll just highlight two big milestones on this. First one is on the construction of the first big wind farm using suction caisson jackets that was built in Germany by Ørsted. And the second one is on the publication of unified guidelines that brings together Eurocode, DNV, ISO, but also all the academic knowledge that's been required to date. And I think that's the first time that people come together and really agree on a design method. So I wanted to highlight that. And if you're interested, you can go read that document, but also read the Fleming Award of this year, which was on the design of suction caisson. All right, and obviously there has been also quite a lot of work done on pin piles, but it hasn't been the main focus over the last year. And finally, applying to all of those foundations is the introduction of monitoring and AI techniques to create digital twin of the structure that can enable a more efficient and safer maintenance of the wind farm, as well as life extension. And there is very little published in that spectrum at the moment, but there is a lot of research going on in the labs, and I suspect that this is going to become really, really important over the next decade or so. So that's all well and good, but that's very European focused. And as Zack mentioned, we're now expanding to other site locations, and that comes with new challenges. All right, that animation is not working. So Zack covered really well new soil conditions and improved site investigations, so I'm going to pass on these. But the last bit that's important is to be able to design to earthquake loads. That's particularly important for East Asia and North America. And that's the best way to go about that is probably to do some centrifuge modeling, but dynamics this time. And there has been a lot of work going on in Cambridge, but also in Delft University that I'm aware of. I'm sure that there are other projects looking at how the foundation behave. What I've chosen to talk about today is something that you may not have considered, which I find really fun. It's work that's been done by a PhD student that I co-supervised in Cambridge, and who is doing tests to evidence the behavior of scarab protection under seismic loads. And that's an exemplar of one of his tests pre and post the test, and showing how the scarab protection has settled with the earthquake load. Right, and that brings us to today as research on fixed bottom structure. As of a few months to a couple of years ago, the first floating wind demonstrator became conclusive, and we're at the stage now where we were for fixed bottom maybe in 2011, 2012, where the technology is ready, but it's not commercially viable, and we need to scale it up. And this comes with a whole bunch of challenges. So just before I dig in, for you to get a sense of how massive floating wind could be and how important it is, this is a map of the world with everything in dark blue being water depths above 80 meters, where we've not yet been able to install bottom fixed structure of the type shown on the diagram at the top. And this map is a map of the wind speed across the world. Everything that's in light blue is because we don't have the data, but everything in dark, the greener, darker the color is, the more it blows basically, and the more energy we can produce. And this is what happened when we superimpose both graphs onto each other, showing how much untapped wind energy there is. So to be able to access those water depths, I think floating is very much needed. And we're at a stage where prototypes have been conclusive. This is an exemplar of the prototype that was used off the coast of Portugal. It's called WindFloat, but there has been different platforms that have been developed. And up to today, the main challenge was to be able to develop those floaters and make sure that they were stable enough. And I don't think geotechnical engineers were super involved up to today. But the problem is that if you put, say, 3 to 6 mooring lines to each of those floater, then you end up with 3 to 6 anchors. And as you multiply that by 80, that becomes quite a lot. And that means that you need the time to install all of those, and then you need to manufacture them. So one very simple way to cut down cost is to share those anchors between the different platforms. And this comes with the added difficulty that if one of those anchors fail, you will have a risk of cascading failure. So we need to be able to understand precisely how those anchors are going to behave under combined multidirectional loading, and be able to predict their behavior and provide design guidelines that are robust. There are different types of anchors that exist, all probably borrowed from the work that has been done in oil and gas before, with traditional anchors and others that are more developmental and gaining momentum. And here in Nantes, we have 2 big projects currently ongoing, Mutank and ShareWind. ShareWind is looking at suction anchors in clay under combined loading, and it's a project that's funded by the European Union through a Marie Curie Fellowship to Christian Soriano Cabrera. And then the Mutank project is the one that I'm going to be talking about, is looking at piles under multidirectional loading. So this is, again, a joint industry project that's funded through France Énergie Marine, in which University Gustave Eiffel is very much involved, and involves many industry partnered, and is managed by the National Research Agency for 2030 French goals on renewable energy. And the objective of this project is to explore the viability of using shared anchor as a means to lower the cost of energy. So the idea is really to understand how anchors would behave in multidirectional loading condition, and then see whether the excess in geometry that's needed for those anchors, if there is any, is leveraged by the cost that they're unable to save. And that's articulated through 4 work packages. The first one is to establish the loads on those systems. The second one is to develop a geotechnical model through 3D finite elements modeling to elucidate the behavior of those anchors. And the third axis is to develop centrifuge tests to validate those models and to validate the failure mechanism that we're seeing in the 3D FE. And finally, the last work package will cover cost and finally answer the question of the objective. So Mathieu Blanc and myself are in charge of that third work package, with a postdoc doing work on this called Ricardo Zapata. Why is it not going? And our aim here is to produce reduced scale centrifuge tests of a pile that's loaded in different direction, and to elucidate the failure mechanism and the behavior of the pile under this combined load. And if you're interested in that work, the first paper on this will be published as part of the 5th European Conference on Physical Modeling in Geotechnics, which is under the ISSMGE umbrella as well. And that kind of concludes my talk. In summary, as Phil said at the very beginning of this event, research in offshore geotechniques has been very important, but is also at a stage where it's very exciting. It's here to stay, and we're waiting for the next exciting development in the field. Thank you.
Christelle, you
Yes.
took more time than usual, but it was so exciting and important. Thank you very much.
Thanks.
You covered and you complemented what Elizabeth was saying and everyone. Great work. I'm going to share my screen quickly before I give the floor again to Phil for his concluding slide. So I'm sharing quickly for you and the viewers what I have done in the 90s as a PhD student. In the past, you know, we did static solutions for rigid piles and flexible piles depending on the transfer length. So if you take the material properties of the pile and compare it to the material property of the soil, you get an L0, which is a transfer length. And if the transfer length, if the length of the embedded pile is less than the transfer length, the pile is expected to behave as a rigid pile. Like Elizabeth was saying, a gap on top and a gap in the bottom when the pile moves into the rock, because it's so big in diameter. Case of flexible pile is when the length is more than 3L0. And there was always a missing link. Well, if you take the discrete element modeling, my PhD, Elizabeth, was solving the 4th degree differential equation. And I'm showing you this because it's funny to see that the solution typed in font 16 was 33-meter long. And I made the workers, because I was a contractor also, carry the equation. And you can see it here, the workers feeling their work with 33-meter long pile and the model. Can you guys hear me?
We can, yeah. Thanks, Marc. Would you like me to wrap up?
I don't know what happened, but I wonder if you saw the screens.
We did, yeah. We saw your screens.
Yeah, thanks for sharing, Marc.
So in 1994, the solution was developed, and it was best paper of the year at the time. It was developed 92, and I used it 2 times in the design of onshore monopile foundations. I was so excited with your presentation that I had to tell you this, because I'm known to be a contractor, but in the back, I was a pure theoretician. So now, Phil, you're the leader of TC209. Don't tell anyone, but this episode of all the others. Thank you so much. The floor is yours for the concluding slide.
I'll wrap up very quickly. So hopefully everyone has enjoyed the talk. Just a close from me, a couple of key points. Takeaways, I guess, offshore wind, it's clearly here to stay. Geotechnics plays a critical role in project success. There's much that's been done, but there's much more still to do. It's an exciting time. And if anyone out there who's watching this, if they've lasted this long through the talk and they're keen to talk to TC209, reach out to myself, any of the other presenters here, or indeed any of the other 100 members of TC209, and we'd love to welcome you into the circle. Before I just go to the last slide, my own thanks as well to Elizabeth, Zack, and Christelle for great talks and for stepping up and getting involved tonight. Really appreciate it. And just to finish on the closing slide, as a reminder, see you in Nantes next year for the 5th Symposium on Frontiers in Offshore Geotechnics. Again, reach out. We'd love to see as many people there as possible. It will be an exciting conference. Even bigger, Marc, I'm sure, than the one in Austin, although I'm not sure anything can be bigger than a conference in Texas, but I'm sure we can try. So we hope to see you there, and we hope to see many of the viewers. That's it.
Thanks, Marc. Thanks,
I
Phil.
will definitely do my best. I will definitely do my best. Thank you all. It was a great episode. Thank you for giving ISSMGE your time and take part in this IITT series. I like to thank also Philippe Jean-Jean, who relaunched TC209, and he's my classmate. And see you all in Nantes.
Thanks,
Bye,
Marc.
France.
See you in Nantes.
See you.
Bye.